So from the video we saw that most reactions are reversible, so that's that first blank. White's not going to work, is it? So most are reversible, meaning the forward and the reverse reaction could happen. Okay, so the forward reaction we would say A2 plus B2 yields 2AB. Okay, if we were going to read it as a reverse reaction, we would say 2AB yields A2 plus B2. Okay, the way that we recognize if something's written as a reaction and it's reversible is by this double-headed arrow. So the double-headed arrow shows reversible. And on a test or a worksheet, it might show up a little bit different depending on how the font works. Sometimes you'll see it like this. Sometimes you'll see a full out arrows on top, and then sometimes you'll see this way and this way. So just recognize both, all three of those as different ways, and it really just depends on the font that they're able to use. Some things will have a double-headed arrow, some have to do two separate arrows, just depends. But the double-headed arrow shows reversible. As time passes, the rate of the forward reaction will decrease, and the rate of the reverse reaction will increase until the two rates are equal. And at this point, when they're equal, is what we have known as chemical equilibrium. Okay, and the video kind of showed it. You have the forward and the reverse reaction happening. May not be 50-50, may not be 50% of each reaction, but they're happening, and the changes may not look like something's happening, but at the molecular level, you actually have both reactions going on. Okay, and it looks kind of like this. Okay, so starting out, my forward reaction starts high, and of course it starts to decrease over time right here. And then the reverse starts to increase until you have this equilibrium established about that point. Okay, and if you noticed at that point, your concentrations are not necessarily equal of your products and your reactants, but they are constant. So that this gets to be where the concentrations are remaining the same throughout the rest of the time once equilibrium is established. And then this is just kind of a visual. When you are at equilibrium, you have opposing processes happening at the same time. Okay, and we talked about this a little bit when we talked about phase changes, and that's why at phase change, remember the temperature is constant, and that's because at that exact temperature, let's say 0 degrees Celsius for water, you have the same number of molecules that are freezing as you do melting, because that's the temperature at which ice melts, but it's also the temperature at which water freezes. So that's why if you're exactly 0, you have that equilibrium going on. Now, if you go much below 0, then it'll all freeze, or if you go above 0, it all melts. But at the phase change, that's one of the reasons why it is constant, because at that time it's in equilibrium. You got to give it either take away some more energy for it to freeze all the way, or add more energy for it to melt all the way. We already stated that the reactants and products are not necessarily going to be at the same concentrations. However, they will be constant at equilibrium. And this kind of shows that as well, the forward rate and the reverse rate, and then we're talking about the amount. So no change in amounts when you reach equilibrium. But if we shift the equilibrium, that is different, and that's going to be what your worksheet's about today, because it's not really that hard to understand equilibrium, forward and reverse happening at the same time, but not everything remains at equilibrium. So there's something called Le Chatelier's principle that we're going to talk about, and that is a system that is at equilibrium, so it's reached equilibrium. If it is disturbed, or if we stress the system by making changes, it will make adjustments to restore that equilibrium, and the system is said to shift. Okay, and it will shift either to make more product, or it will shift to make more reactants in order to reestablish that equilibrium. So when we're going through this, when we say shift right, that means we are favoring our products, meaning more products would be made. That says product, I ran out of room. If I shift left, that means I favor my reactants. Okay, and then no shift means no change. So equilibrium doesn't change. And there's a few cases where we have no shift. Okay, so let's talk about the things that will add stress to the system. These 4 things will affect the equilibrium. We have changes in concentration, temperature, pressure, and the presence of a catalyst. If we are talking about all of those except for one, they apply to all systems. But changes in pressure will only apply to what? What's the only type of system that pressure will have an effect on? Gases. So only affects gases. We'll just say gases only. The volume, I mean, any of those other, like liquids and solids, pressure has no effect on those. It's just gases. Okay? So let's talk about concentration first. Okay? Changing the concentration of either the reactant or the product will cause a shift in the equilibrium to minimize that change. So if I increase my concentration, the equilibrium will shift away from that increased species. So if I increase my reactant, it will shift away from it and go towards product. But if I was to increase my product, it would shift back to the left in favor of the reactants. So you just have to look at what's being increased. If I decrease the concentration, it will shift toward the whatever was decreased. Okay? So let's look at an example. So if I have this particular reaction, I have H2 plus iodine, it makes hydrogen iodide. Okay? So if I were to decrease the amount of a reactant, so I could choose the H2 or the I2, if I was to decrease it, meaning I take some out, which way would this equilibrium shift? Toward the left or the right? If I decrease in a reactant, remember if I decrease, it shifts toward what I'm decreasing. So it would actually shift left, which would favor my reactants. Meaning I would start to make more reactants. So what would happen is the reverse reaction would be favored, which would mean shifting it to the left. That should have been a double-headed arrow there. I didn't realize it wasn't. Okay, so it would shift back towards, so it would shift this way, the reverse, and start making more reactant. What if I were to increase the reactant? It would shift right, because when I increase a concentration, it shifts away from it. So for the reactant to shift away from that, I'd be shifting right. So that means I would favor products. So that means more HI would be formed. Okay? Does anybody have any questions on concentration changes? Okay. Then we have changes in temperature. Okay? And with changes in temperature, it's going to be kind of actually like the reactant, increasing the concentration. So if I increase the temperature, the reaction will shift away from where the heat is in the reaction. If temperature is decreased, it shifts toward it. Okay? And remember, in a thermochemical reaction, you have to either treat heat as a reactant or a product. Okay? So remember, when delta H is positive, is that endothermic or exothermic? Does anybody remember? Endothermic. And if it's endothermic, how did we treat heat? As a product or a reactant? Remember, I'm having to add heat. So where should it go? Reactant or product? Reactant, yeah. So it would be a reactant. If delta H is negative, then we have an exothermic reaction. And I would treat heat as a product. And you need to know that because sometimes it'll already have the heat either as a reactant or a product. And sometimes it'll give you delta H separately. On your worksheet today, there's one where it gives it to you separately. So you have to decide, is it endothermic or exothermic, so where does heat go? And then you can answer your questions based on temperature. Okay? So let's do a couple of examples of those. So in this case, I have heat plus carbon, and carbon dioxide is making CO. First of all, before we answer any question about temperature, is this endothermic or exothermic? Heat is a reactant, so it's endothermic. Okay? So it's endothermic. So if I were to decrease the temperature, would this reaction shift to the left or shift to the right? If I decrease temperature, it would shift left. So that means I would favor reactants. So as time progressed, this would mean I would make more carbon in CO2 because I'm shifting to the left and favoring the reactants. What if I increase my temperature? It would shift to the right and then favor products. Okay, so that means as time progressed, the concentration of CO would increase. Okay. Do you want me to add in an exothermic reaction? Because it is different whether you have exothermic. On this one, you can't just look at it and say, oh, decreased temperature is shift left. If it is a exothermic, if I decrease the temperature, it would shift right, so it's opposite. Okay? So you can, if you want to, if you don't want me, do you want me to do an example, or you want me to just, okay, that's what they wanted last period. Okay, so I'm just going to do a pretend equation. I'm going to say A plus B yields C plus heat. Okay, so since heat is appearing as a product, we have an exothermic. So now if I were to decrease temperature, which way would it shift? Okay, it would shift to the right because it's going to shift toward the heat. So this would shift right, and I would favor products, meaning I would make more concentration of C. And then if I increase temp, it would shift which way? Left. And that means I would favor reactants, and that means my concentration of A and B would increase, right? Okay? So this is actually not hard, it's just you gotta stop and think about it. Okay? So I think that brings us to changes in pressure. Is anybody still writing before I move on? So when I'm changing the pressure, we said earlier pressure affects, changing the pressure will affect the gas only. Gases only. Okay? And that's because volume of is not affected when you have a liquid or a solid. Okay? So, and this one, if there are equal number of particles on both sides of the equation, there will be no shift. Okay? And when we're looking at equal number of particles, we'll be looking at the moles of gas. Okay? So, if you have non-equal number of moles on each side, if the pressure is increased, it will shift toward the side with fewer number of moles of gas. Okay? If the pressure is decreased, it will shift toward the side with more moles of gas. And when I am looking at a balanced equation, how will I know how many moles of gas each side has? What would I look at? The coefficients. Very good. You would look at the coefficients. Okay? Alright, so let's look at some examples. Again, this is not something you can say, oh, if I increase it's going to shift left, or I'm always going to shift left, or it's always going to shift right. You have to look at the number of moles of gas. So when you see that they're asking about pressure, you need to decide how many moles of gas on each side. So on the reactant side, how many moles of gas total do I have? And it's asking about total on each side. So I have 2 plus 1, so I have 3 moles on the reactant side, and it decreases to 2 moles on the product side. So now I can answer my questions about changes in pressure. So if I were to increase the pressure, what would happen? It would shift to the right because there's fewer moles of gas. So we'll say fewer moles of gas. So that means I would favor my product. If I decrease the pressure, what happens if I decrease the pressure? If I decrease the pressure, it would shift to the left because it shifts to the side with more moles of gas. And then that means, so that had more moles. So that means I would favor my reactants. Now, if I'm talking about a system that's all gases, what would changing my volume, how would it affect it? Okay? Because if I increase my volume, what did I just do to my pressure? I decreased pressure. So if it's asking about volume in gases, think of it in terms of pressure, because remember, they're indirectly proportional. So if I increase my volume, that means pressure would decrease, so then I would go to more moles of gas. Okay? If I decrease my volume, then my pressure would increase, so then I would use it to the fewer moles of gas. So you got to think of it that way, because it affects it in that direction. Okay? And then the last one is easy, and that is catalyst. What did we say catalysts were? Enzymes in your body, but what do they do to a reaction? They speed it up. They allow an alternate pathway. So what do you think catalysts would do to an equilibrium? Which way do you think a catalyst would shift an equilibrium? It's a trick question. There's no shift. Okay? It's a trick question. It will not shift the equilibrium. Okay? And that's because, if you remember, when we looked at the diagram that had a catalyst in there, the amount of reactants and products didn't change. It just lowered it. So what it does do is it allows you to reach equilibrium faster. So you will reach equilibrium faster, but it does not affect the equilibrium position. So you will reach equilibrium faster, but does not affect or does not shift it. And of course, same thing with an inhibitor, it would just be the opposite. It would take longer to reach equilibrium with an inhibitor, but it does not affect the equilibrium position. Okay? And then I think it's left off on my slides, but your last summary of chemical equilibrium in your notes says at equilibrium, the concentrations of all the substances become, and what do you think that blank is? Not equal. Look at the graph underneath. They're not equal, are they? They're constant. Yeah. So that last blank is constant. And of course, I said again down there about the double-headed arrow to make sure. Okay. And then I just gave you a couple of last little summaries. Okay.